Hello and good morning, everyone. I'm audible? Yeah. I hope you are all doing well. On behalf of Vishwakarma, the official mechanical engineering department of VIT Pune, I extend a warm and heartily welcome to each and every one of the you. So today we have gathered here to celebrate the second episode of our flagship podcast series, Engineering Blueprint, a series where we bring you inspiring stories straight from minds shaping the future of engineering. And trust me, today's episode is extra special because we have with us a remarkable individual, a VIT Pune alumni, who has walked the same corridors with us, attended the same lectures, and faced the same career dilemmas. But what sets him apart his incredible journey from VIT Pune to the prestigious Indian Institute of Science, like that means IISc Bengaluru, and working with the global industry leaders like John Deere and Siemens Technology. So today's takeaways are the transition from industry to research, how and when taken the leap, the inside view of IISc Bengaluru, what makes its hub of innovation, a sneak peek into space technology and research, and exciting projects shaping the future. Lessons from working with Siemens Technology and John Deere. So, if you have wondered about pursuing higher studies, stepping into the world of research, or making impact in the industry, this is a moment to learn from someone who has been in your shoes. So, with no further delay, I will welcome our guest, Mr. Rohan Kulkarni, and I would like to Rohan to kindly guide our students. Thank you.
So, good morning, everyone. I'll be talking about uh, role of mechanical engineering in space technology. So, I'll be going through a broader perspective of why one should explore space technology and what we do at IISc in contributing to this wonderful domain. So, we'll start with why we explore space. Why do we have to explore space? I'll be only talking about the technological aspects uh, while delivering this presentation. So, first is technological advancements. Technological advancements like additive manufacturing, material studies, and autonomous systems. These are the things that we end up developing and innovating while exploring the space, because space is something that comes under the extreme environments, and it pushes the human boundaries uh, to design and develop something more. Another aspect is it is not just limited to the outer space, but it is also related to the earth that we live on. So it so so another important aspect is earth monitoring and climate studies. So there we get to learn about satellites, earth observation sensors, structural dynamics, and orbital mechanics. Then comes the resource exploration. So as we know, like NASA is already planning to build a colony on Moon by 2030. So we'll obviously be exploring the resources that are available on the Moon and later on Mars. So what are the resources that we have? The one of the resources that is present on Moon in abundance is regolith. So what is regolith? So regolith is nothing but the outer layer of the rocks that are present on the Moon. So this regolith is nothing. In loose terms, we call it sand. So this is one of the important resources that we have on the extraterrestrial sites. Another thing is autonomous rovers. These rovers will help us explore these resources by without actually going to the sites, but by just simply staying on our homes and Earth. Another one is the habitat building. So I'll come to these terms in detail in later slides of my presentation. And the another important aspect is the national security and global influence. So the space exploration helps us in building military satellites, hypersonic vehicles, and orbital debris mitigation. So what can mechanical engineers do while exploring the space? First is structural design. So we have to contribute in designing spacecrafts, designs for extreme conditions. When I say extreme conditions, it it comes under extreme pressures, extreme temperatures. Then comes deployable designs, like compliant mechanisms. So ISRO and DRDO are currently funding tremendously in developing the deployable designs. We call it in technical terms compliant mechanisms. So these are the mechanisms that do not have any rigid links, but it is a single piece mechanism where you have the members that can bend, that can flexure, and that can undergo torsion to deliver the desired outcome. Another comes is the propulsion systems, where we need to investigate into the engines and fuel systems. Then comes the most important part, that is manufacturing and materials. So additive manufacturing is one of the important aspects that almost all the universities and industries are uh, digging into. The another important aspect of additive manufacturing is the in-space manufacturing. So you don't have to actually uh, uh, take the labor to the extraterrestrial sites, but you can simply do the in-space manufacturing without any human intervention. So that is nothing but the additive manufacturing. Another thing is habitat engineering, then in situ resources utilization, then manufacturing in microgravity, because in outer space you'll have to deal with the gravities that are like 1/6 or 1/3 of the Earth gravity. Then comes the robotics and AI part. So this will be under the automation and the uh, rover building systems. Another thing is microgravity studies, because like in microgravity there are so many effects that are happening to the human body and the other system that we usually build on Earth. So the life sciences experiments are very crucial, that need to be performed under the microgravity. So we cannot simply go to extraterrestrial space and carry out these experiments. But what we do here is we build the microgravity simulators. You must have heard about the drop towers, parabolic flights, then magnetic levitation. I'll be covering one more microgravity simulator, that is called clinostat, or the random positioning machine, that we have built in our lab, and we perform some of the biological experiments uh, in the simulator and try to get the data. So I'll come to the important part, that what we do at IISc. So in our lab, so we work with functionally graded materials. It comes under the domain of materials engineering. Then we do the microgravity studies. We have built the clinostat and random positioning machine. Then we have built a biological payload. We call it MANAS, but the full form of MANAS is microbial analysis in space. Then comes the space bricks. So these are nothing but consolidation techniques for regolith, additive manufacturing, and bricks repair techniques. Then comes the habitat engineering. We design and develop the modular habitat for astronauts, and we perform the structural analysis on the designs that we have built. So I'll go one by one. So, by the way, feel free to interrupt me at any point you feel you're not understanding what I'm talking about. So I'll go one by one. I'll start with the functionally graded materials. So what are the functionally graded materials? So they are so we intentionally bring the variation in composition or the structure within the specimen volume. So this leads to continuous change in material properties such as strength, hardness, and thermal conductivity. We performed one experiment in IISc where we used a technique called friction stir processing to manufacture these functionally graded metal matrix composites. So what we did is we have something called polymer derived ceramics. So these are basically polymer particles, but when you heat these polymer particles at high temperatures around 800 degrees Celsius, then the organic part of the polymer evaporates, and what remains is the ceramic. So this ceramic acts as the strengthening component in your metals. So that's why we call it metal matrix composites. So we distribute these polymeric particles within the material, and at a in a particular pattern along the dimensions of the component, and then we uh, do the pyrolysis. Pyrolysis is nothing but heating at the desired temperature. So once you do the pyrolysis, the organic part will evaporate and you get the metal matrix composites. So I developed one functionally graded material where I tried to vary the strength of the component along the thickness. So I use the modified Klein model to theoretically determine the strength of the component, and it basically works on the principle of strengthening. You must have heard about the. I guess all of you are mechanical engineers. You are listening to me, so you must have heard about the strengthening mechanisms. So one of the strengthening mechanisms is by obstructing the dislocation movement. So you obstruct the dislocation movement in a desired manner. So that ends up giving you a functionally graded material. So the result that I got was something like this. So strengthen the megapascals, I'm putting it on y-axis, and the thickness I'm putting on x-axis. So if you see, I used the aluminum alloy 6061 and perform some experiments on it. So if you see, you can see the variation of strength along the thickness of the specimen. So from 240, around 240, I reached around 260 within the thickness of 3 mm. Then another thing is the clinostat. So what is a clinostat? So it is one of the microgravity simulators. So this common simulators that we microgravity simulators are drop towers. So what do we do in drop tower? So we drop our payload in a hollow tube. That tube is around say six story in height. That is one of the drop towers is there in IIT Madras. So, but the problem with that is it ends up creating a hypogravity. It so there is a chances that your payload might get damaged, and the major limitation of this microgravity simulator is that it can create gravity only for a few seconds, say 9 seconds to 20 seconds. But this is a clinostat. This can create microgravity for hours, for days, and even for weeks. So what does it do? So it has two rotating axes. So I think you might be able to locate the two motors that are there in the diagram as shown, motor 1 and motor 2. So the motor 1 is what drives the outer frame, and motor 2 is what drives the inner frame. These two frames rotate simultaneously. What it does is it does create time averaged microgravity. So if you try to get the real time graph of the acceleration components, so you will never see the acceleration components going to like literal zero. But if you take the time average of those components, you will see the time average is tending to zero, but not exactly zero. So you will be able to achieve a gravity of 10 to the power minus 4 to 10 to the power minus 6 g. So what it does is uh, these these two frames are rotated independently, the outer frame and the inner frame. So the specimen that is in this diagram, it is written millifluidic payload. So the specimen experiences gravity in all the directions. So if you try to map the resultant acceleration along the surface of the sphere, you will find that this vector traces the entire surface of the sphere if you have optimized the clinostat completely. So so if you take the time average of these components uh, that are distributed along the surface of the sphere, the time average will eventually go to zero. So in a clinostat, these rotations RPMs of motor 1 and motor 2 are kept constant. Whereas in random positioning machine, these RPMs are continuously varied uh, uh, in magnitude as well as in rotation. So no path is traced again and again that helps us tracing the gravitational vector along the entire surface of the sphere. So if you see, we have some results that we have got. So on my left is the simulation, and on my right is the experimental results. So if you see, the time average acceleration always goes to zero once it starts rotating. So one of the biggest challenge here is the optimization. So you have to optimize the RPM according to your dimensions of the component. Another thing, if you are performing in the random positioning machine mode, then you have to develop an algorithm so that you don't get any jerks in the system. So if you get the jerks, that will decrease the quality of microgravity that you are getting. So if you see on the experimental graph here on my right, so that graph is not exactly as same as the simulated graph. Why? Because we experienced a lot of vibrations while performing the experiments. So vibrational analysis is one of the important aspects that comes into the picture when you're dealing with the cryostat. Uh, Another thing, we perform these experiments on a bacteria called E. coli. So if you see, if you can see these two graphs. So these two graphs have shown that we perform the experiments for 2 hours and for 3 hours. So if you see in clinostat, we saw that the growth of the bacteria is more than what we get in the normal gravity situations. So why is that? So a bacteria undergoes a living cycle that contains a lag phase, then growth phase, then steady phase, and then death phase. So this lag is where so after completing the lag, you can see that the bacteria will start growing. But what we observed here is in microgravity situations, the lag phase decreases. So the growth starts immediately once you start exposing the bacteria to the microgravity environments. So this is one of the interesting results that we have got through these experiments. We are performing these experiments on a bacteria called 𝗍𝗑 and the stem cells. So what are stem cells? Stem cells are nothing but the human cells, human muscle cells. So why do we need to study human muscle cells under microgravity conditions? Because once the astronaut go to the space, they experience the deterioration in their muscle mass. So this is one of the important aspects that we need to study. If any of the astronaut is going to space and he'll need a treatment so that he can prevent the reduction in his muscular mass. And so eventually we are performing these experiments with the help of ISRO, and then we'll be soon be publishing some of the data so that everyone can read what is going on in the human muscle cells under microgravity conditions. Then comes the biological payload. So we are developing a payload. We call it lab on chip device. So it's a very small device that we are developing in our lab. It's a payload where we have a bacteria in the device in a cassette. We provide some nutrition to the bacteria, and then we perform these microgravity experiments. We perform these experiments under the various temperatures and pressure conditions so that we get feel of what's going on in the extraterrestrial sites, say Moon and Mars. So what does this bacterial biological payload contains? So it has cassette that contains the host species like a bacteria or something, then the control and data handling unit. So you need to continuously monitor the growth of the bacteria. So for that you need the controls, like you need to provide the nutrients to the bacteria. Then you need optical density measurements so that you can you can real time monitor the growth. And then you need to have, once you get this data, you need the data handling units. After that, you need external storage to uh, to get this data. Then you need ground situation, you need the comparison with the ground situation. So you have to do the real time comparison with the what is happening to the bacteria in macrogravity conditions and what is happening to the bacteria in normal gravity conditions. Then comes the monitoring and diagnostics. If something goes wrong in your payload, you need to you need to diagnose that, and so you need to provide some alternatives so that your experiments won't stop, because the response time of the bacteria is in days. Like, it starts growing after 24 hours or 2 days or something like that. So this is the bacterial biological payload that we have built. On my right, it's showing a cassette. It's a fabricated device. So in this acrylic cassette, we have a bacteria, and this is the entire control system that we have built on it. Excuse me. So what does this entire thing contain? So it has a cassette that contains fluid channeling, spore management. Spore is nothing but the eggs of the bacteria. This is what we call. Then pumping mechanism. You have to pump the nutrients to the bacteria. Then sensing. You need some LEDs and diode, and then periodically you have to query like what's going on. Then comes the cartridge. It has multiple cassettes built in it. Then it has motion integration system, synchronized actuation, board level logic, data transmission, and storage devices. Then comes the housing. So in housing, you need to perform vibrational analysis, wiring management, dynamics, like because it will be undergoing some vibrations that will produce some high G. And then obviously the weight management, because it will be going to the outer space one day, and uh, like transporting even even 1 kg to outer space costs a lot, uh, like a lot. So the device that we have built is set to fly with the Gaganyaan mission that will happen soon in later this year. So if you want to read more about this, you can read the paper that I have cited uh, at the bottom of my screen. So you can search for it and read about the device in greater detail. So then comes the space bricks part. So why do we need space bricks? So we have bricks on Earth. What we do with the bricks? We build houses using those bricks. So similar things will be needing on in space, on Moon, on Mars, where we'll be needing to build the bricks and build the houses for ourselves. So we invented two techniques by which we have built these bricks. So in our lab we have this soil simulant. So we have the soils that mimic the soil on Moon and Mars. So we play with these soils and we experiment and we try to make new things out of these soils. So we have developed two techniques that help us consolidate the loose soil. First is microbially induced calcite precipitation. We call it MICP, and second one is the sintering process. So in MICP, what we do, we have some bacteria, we give some nutrients to bacteria, and we then put this into a soil. Then after 5 days, this bacteria secretes calcium carbonate, and this calcium carbonate covers the entire surface of the loose soil and forms the consolidation. So this we have reached a strength of 5 megapascals with just by using a bacteria, which is almost comparable with the strength that we have on at our bricks. These are the bricks that we use on Earth. So these bricks give us a strength around 20 to 30 megapascals. Another technique is called sintering. So in sintering, what we do, we have a soil simulant, we use some polymeric binder, then we compress this mixture under a load, and then we keep it in a furnace at near melting temperature. So this thing we have performed, and we have reached a strength of 55 megapascal using the lunar soil simulants. If you want to read more about this, I have again cited one of the papers from our lab. You can take a screenshot of this and read this paper in greater detail, so you can understand you can see what is actually happening on micro scale, and like how the microstructure is evolving in these two processes for the soil. So these bricks that we have built are actually machinable. So you can put them on lathe, and with a cutting tool you can give the give it a shape uh, as you want. So I have shown these two pictures where we have uh, machined the brick. So on the picture B, you can see a machined sample and unmodified sample. So this MICP method that we use, we use bacteria in it. So if you apply this slurry that we have formed with the MICP method, and if you apply the slurry on the broken bricks, your bricks will will be repaired. So we have recently published a paper where we have extensively explained this repairing method, where you can actually control the damage that has been caused due to micrometeorites uh, on your space bricks. Then comes the application of additive manufacturing. So this is my project that I'm currently working on. So additive manufacturing helps you build the lightweight load bearing structures. So you must have heard about the meta materials. So what are these meta materials? So for a material, your properties are dependent on the material that you're using. But for metamaterials, this is the property of the structure that uh, you are actually building. So in uh, in our lab, we have built a customized dual 3D printer where one nozzle extrudes the slurry while the other nozzle extrudes the scaffold. So scaffold is nothing but the support system necessary for the overhangs or something like that. So I'll show you a video of single nozzle extrusion here that will give you an idea of how the soil slurry is extruded. So I hope the video is visible to you guys. So this is the 3D printer that we have built in our lab. So using this technique, you can actually build these structures as you want. You can. This is just a demo that I'm showing, but we have built two-dimensional meta materials using the same system. Then comes the habitat engineering. So what is a habitat? Habitat is nothing but the houses that we built on extraterrestrial site. So in our lab, we proposed a modular-based habitat design. So we put a constraint on that the individual elements of the habitat should be stackable, so that the volume consumption when you are transporting the system from Earth to the moon reduces. So we have used a principle called modularity. So you can actually dismantle this big habitat into smaller pieces, and uh, then join these simple pieces and build the houses for yourself. So this thing is still under supervision, and we are still working on it. So we have actually used the panel based modular architecture that would function as standalone pressurized module. Then becomes the important aspect like material selection, because you have to deal with the problems like micrometeorite impact, pressure differences due to lack of atmosphere. Then the structural, you have to study the structural rigidity of each module. So you have to perform FE analysis, numerical analysis, and you have to validate these analysis by analytical models. But you cannot simply build these structures the way you want, because you have to adhere to the standards that are posed by the NASA. So what we have done in our lab, we have simulated this entire habitat environment with the virtual reality. So you can code into Unity, and it's a C++ code basically, where you can actually simulate the entire environment that is on moon. And then you can also build the habitat on it, and then you get to experience what is happening exactly on the moon. So this is the mod. These are the models that we have conceptualized in our lab. So I have again cited one of the papers here that we have recently published. You can read this in detail, so you get an idea about the interiors of this architecture, and what is like you can get to know more about the materials that we are planning to use to build these habitats. Okay. Yeah. So you can. So I suppose this height thing was there even through the entire presentation. Okay, fine. So you can read this paper and get to know more about this habitat design that we have built. So with this, I would like to thank you guys, and this is my group photo. So we got an opportunity to work with the astronaut designate, Group Captain 𝗩𝗏 Shukla. So he's currently at NASA, and he's set to fly to ISS soon with one of their missions. So he's one of the. So you must have know you guys must be knowing about the four astronaut designates that Honorable Prime Minister revealed the names, and one of the astronauts worked with us for his habitat engineering project, and he's soon set to go to ISS. So with this, I would like to thank you all and stop my presentation. So if you have any specific questions about the presentation that I've shown, you can ask me. Also, you can ask me any generic questions that will help you like post graduation or something. So after my BTech, I was placed in John Deere. So I worked in John Deere for a year, and then I left my job. So uh, in my experience, the job gets repetitive after a point. So the opportunities to learn more ceases. So I always wanted to pursue research where I wanted my own freedom to explore things on my own. I was interested in materials and manufacturing, so I chose this path. I appeared for GATE, and I fortunately got into IISc, where I got to work with these technologies. And then in my MTech, I had no plans of pursuing PhD actually, but then I talked to my guide, and then he proposed an interesting project where we were working on this habitat building and the space in e-space manufacturing. So that inspired me to join PhD program at IISc again.
Okay, can I ask my question?
Yeah, sure.
Okay, so hello, sir. That was really amazing session. Because I'm a space enthusiast since my childhood, and I really want to enter in this field, but I don't know how to start. Like, can you tell what can be the initial steps? Like I can take right now. I'm in second year, so that can I enter in this field?
Yeah, sure. So what you can do is you can aim for the institutes uh, that are famous for working in space technologies. So some of the institutes are there in India, like IIT Madras and IISc, because we closely work with the ISRO people. And then if you go abroad, there are institutes like Caltech, Princeton, where the extensive research work in space domain is happening, because their partners are usually ESA and NASA. So you will definitely get better opportunities than India if you join these institutes. So there are. I'm guessing you are in mechanical engineering program.
Yes, yes.
Yeah. So in mechanical engineering program, there are lots of opportunities in manufacturing. Like I said, additive manufacturing one of the booming areas that engineers are working on. Then if you are interested in robotics and AI, that has tremendous applications in space engineering. So you can actually get these skills and apply in the field that you want to work in. So you can join IISc for internships. So, like in our lab, we hire interns regularly. So you can join our lab and work with us in the space engineering programs, and then you can join aerospace engineering if you are interested in a to work under a particular professor or something. You can write a mail to that professor saying that you want to work in this area and you wish to join from this date to this date, and then simply wait for the reply or else you can contact me after this session. Then we currently have some vacancies in our lab also. So if you are interested to work with us, then just let me know. Then we can talk separately after this session. No, I took 1 year gap to because I left my job and I took 6 months of gap to prepare for gate. After that, it really gets difficult to prepare alongside the job that you're doing. So if you have to appear for an interview, then I would say just stick to the basics, because these people will not expect something big from you. These questions will not be standard as gate, because these questions are on the spot created. So you just stick to the basics. So I would say you read only the reference books for your while you are in engineering. You try to solve the problems that are given in these reference books. So these reference books will give you an idea, like how to approach a problem and not just to solve the problem, because solving is not important. Once you know how to approach the problem, you will end up solving it eventually. But you should know the ways to solve this problem in different, like there could be multiple ways by which you can solve a particular problem. So you should be able to think in all the direction to get to the solution. It's not about just arriving at the solution, because nobody cares like what numerical value you are getting at the end, but it's how you approach to the value is what important. So ISRO doesn't directly come to the campus here, but if you are working in some of the projects with ISRO, then there you have chances of joining the organization directly through your professor's contact or something. So yeah, ISRO doesn't come to the campus placement here directly. So in the long term, like this was the one of the space docking experiments, right? So docking is very important. If you have watched the movie Interstellar, there is one scene they demonstrate the how the docking happens. So what benefits is you get is basically you get an advantage in exploring lunar missions, uh, and then it basically boosts your technological advancements. So, see, these technological advances were not only restricted to the space engineering, but they also help us in developing systems on Earth. So, if you only thinking about space at this moment, then yeah, it's not entirely correct, because similar situations arrive on Earth as well, where you need to apply these engineering techniques. So we use ANSYS for structural analysis. We use COMSOL. We code in MATLAB and C++ and Python sometimes. Python is basically used for data and AI things, but we are not into data and AI, but we deal with MATLAB and C++. And then for CAD modeling, we use Rhino. SolidWorks, anything that is. But what we use is the licensed version of these softwares, because if you want to publish something out of this, then you have to cite the authentic version of these softwares. Yeah, definitely. So as I said, we build this Kalinostatin or the random positioning machine in our lab itself. So it doesn't require any high end engineering. It can be your BTech final year project where you can develop your own random walk algorithm and try to simulate the microgravity conditions. You don't need to experiment on bacteria or something, because it gets very tedious when you start dealing with the biological systems. But you can definitely work on these microgravity simulators. You can also develop your own parabolic flight uh, using some drones or something that can carry your mini payload and simulate the microgravity environments.
Can you hear me actually?
Yeah.
Yeah, by the resources, what I meant was like on ramping, because as a student, we have the at least we know the names of the domains, like what domain we have to understand to get into the space, or what we have to learn. So, and by the resources, because this is like that paradox is because we have so many resources, so many online, offline we can do. We have to find a structured way or structured approach to some topic, to some way. So if there is some structured resource that has been done so that we can go through it, so that would be helpful actually. Thank you.
So one of the biggest resource is the research papers. So uh, you find out the people who are working in space. You go to Google Scholar, simply search ISRO or something, or you simply type the name of the scientist who is working on the similar projects, and you'll definitely find the research paper that he has published recently. This is one of the, because what we do in IISc is we use the techniques that we have learned and we apply it to a given problem. So in our sense, the problem is space engineering. So we apply these techniques that we have learned to this given problem. So just own your skills that you are currently learning, and then choose a problem that you like and simply apply.
Thank you, sir. Thank you.